All right, hello everyone. Welcome to the first part of the video for section 4.5. We're skipping over 4.4 for now. We will come back to it after this, but we're going to go over the stuff from 4.5 first. For today's meme, you may or may not get it if you think about the reference that it seems to be alluding to. You might figure out what's going on, and or if you've taken physics. This might come to you at first, but if not, you can Google it. It's pretty funny once you get it, believe me. Okay, so section 4.5, we're going to look at derivatives and how they affect the shape of the graph of a function. So I'm going to start out by revisiting critical numbers. So we have this function f of x equals x cubed minus 6x squared plus 10. We need to find the critical numbers. Recall that in order to do that, we first have to take the derivative. So take our derivative here of our function. We can use our power rule since this is a polynomial. So end up with f prime of x equals 3x squared minus 12x when we do that. Okay, and then recall that to find the critical numbers, we have to check two things, right? First, have to check or find the values that make this equal to 0. So we'll take our function and set it equal to 0. So if 0 equals 3x squared minus 12x. And we can also check for input values that make the derivative undefined. However, since this is a polynomial function, that's not something we have to worry about, since there's no way that we could plug something in that would make us divide by 0 or take the square root of a negative. Okay. So let's solve this equation with the derivative equal to 0. We can factor out a 3x from the right-hand side. So we have x minus 4. And then we have two things being multiplied here to equal 0. So we can take each and set them equal to 0. So we'll have 3x equals 0 and x minus 4 equals 0. And solving those, we get x equals 0 and x equals positive 4 as our two critical numbers here. Okay. All right, so that was just a quick review of that, and we need this information moving forward. Okay, so let's look at now how these relate to the shape of a graph. And here it says we found the critical numbers. And if you recall, when we learned about critical numbers, what those tell us is the locations of local mins and maxes of the function, right? So we know that at x equals 0 and x equals 4, we're either going to have a local max or a local min. And we want to know, is there a way we can figure out which is which without graphing the function? Because the idea we're going to be moving towards here is being able to figure out the graph of a function using derivatives, and or being able to figure out properties of functions just using derivatives and not using the graphs of the functions. So let's look at how we would do that. So what I'm going to do first is set up a number line. Okay, and for those of you who took Math 141 Pre-Calc 1 with me, or maybe took it from a different professor, Pierce, you may have seen something like this before. We're going to use what's called a sign chart. And so I'm going to mark my two critical values on it. So I've got 0 and I've got 4 here on my number line. And we know that for each of those, the derivative equals 0, right? So at 0, we know the derivative equals 0. And at 4, the derivative equals 0. And then what we want to do is figure out what the sign is on the output values for the derivative in between 0 and 4, for values less than 0, and for values greater than 4. And so the way that we'll do that, first let me rewrite the derivative here. And okay, so our derivative again was f prime of x equals 3x squared minus 12x. So we need to pick values that are in these different intervals to the left of 0, in between 0 and 4, and greater than 4. So for example, For a value less than 0, I'm going to choose -1. And then I'll evaluate the derivative of that. So I'll do f prime of -1, which give me 3 times -1 squared times -12 times -1. And when we do that, let's see, we get 3 plus 12, looks like we get positive 15. Okay? And so what that tells me then is that for all values less than 0, the sign on the derivative is positive. Okay? Now let's do a similar thing for a value between 0 and 4. So let's just say 2, for example. So I'll do f prime of 2. And I'm not going to write that out this time. Let's see, we'd have 4 times 12 minus 24. Looks like we would get -12 as our value there. And so we see that as negative. So we know that for values between 0 and 4, the values of the derivative are negative. And then finally, we have to do a value bigger than 4. So I would say 5. So do f prime of 5. Plug that in up here. Let's see, 25 times 3, 75 minus 60. Looks like we get positive 15. So then we know that all the values greater than 4 are positive, or the derivative values greater than 4 are positive. Okay? And we're going to be able to use this information to figure out whether 0 and 4 represent local mins and local maxes, or local maxes. Now, before we do that, I just want us to reason through. For each of these intervals here, I only chose 1 point, right? And I forgot to write them down. This one was 2, this one was 5. And I said based on that 1 point, I knew the sign of the derivative for all values in that interval. So for example, what I'm saying is that based on the input of -1, the fact that the derivative was positive there, I'm saying that for all values less than 0, the derivative will be positive. Well, why do I know that? Well, let's suppose for a second there was a value out here less than, say, -1. Let's say something like -2, or -2. Let's say like -6. What if the value of the derivative there was negative? Well, if you recall, when we're taking derivatives of functions, they have to be continuous functions, which also means the derivatives have to be continuous. And if we have a value or a continuous function that is positive values and then suddenly changes from negative values. If you think about on a coordinate axis here, I drew on the upper hand right. If I have a function that's go along, output values are positive, 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 and then all of a sudden they become negative down here. But the function is continuous. So what has to happen in between there somewhere? Oh, right. The function's going to have to cross the horizontal axis, which means that at some point it's going to reach 0 again, which means that if the value of the derivative was positive at -1, but then negative at -6, well, it'd have to hit 0 again somewhere in between. But based on the information we have, the derivative only hits 0 at the input values of 0 and 4, so we know that can't happen. Okay? And that's true for all the other intervals as well. So that's how we know that these values here represent all of the full intervals that they're taking the place of. Okay, now let's use this information to figure out what's going on at 0 and 4. I'm going to draw another axis up there in the upper right, and I'm going to label, we know 0 is here, 4 is here. Okay, and let's think about what the derivative tells us. Well, the fact that the values of the derivative less than 0 are positive, what does that mean about the function? Well, that means the slopes of the tangent lines are positive, which means the function is going to be increasing for all of those values. So it might be doing something like this. Then it gets to 0, and it kind of flattens out. That's what the derivative of 0 tells us, or the derivative value of 0 tells us. And then what happens? Well, here between 0 and 4, we know the values are negative, so that means the function starts to decrease. And as it's decreasing, and I should have drawn this picture better, right? So the function starts to decrease, okay? So notice, what does that leave us with at 0? Well, we see that on the left-hand side of 0 in our function here, it's increasing. On the right-hand side, it's decreasing. And that makes 0 here a local max. Okay? All right, so let's do a similar thing for 4 now. Oops. So we know that to the left of 4, the function is decreasing, which I've already got there with the green line. And to the right, it's increasing. So that means the function is going to come along, get to whatever the output value is at 4. It's going to flatten out because the derivative at 4 is 0, and then it's going to start increasing, which gives us what at the value of 4? Well, it looks like we end up with a local min there. Okay? So that's how we can figure out without graphing. And I know I drew a graph, but notice that I didn't actually graph this function in my calculator or by inputting a bunch of values. I just used this information from the derivatives to help me figure out the shape of the function. Pretty cool, right? I know you all just said right. Okay, so let's summarize this information. So let's suppose we have a function f that's continuous over some interval, and there's a critical point that we found in that interval. So in our example, values for c would be 0 or 4. And if the function is differentiable over that interval, except for maybe at c, because if it's a critical point, the function might be undefined there, then it satisfies one of the following. And this is kind of the word description of what we just did. So if the derivative changes sign from positive when the value of x is less than c, and to negative when the input values are bigger than c. So that would be right down here for number 1, that would be the example where we're going from positive, which means we're increasing, to negative, to decreasing. Well, that's where we get a local max in the function. If the sign on the derivative changes from negative when the values of x are less than c, or the input values are less than c, to positive when they're bigger than c. So this is going to be the example now where it's decreasing to increasing. We'll notice that that gives us a local min. And then there are some instances where we'll end up with the same sign on both sides of the critical value. And at that point, we cannot determine whether there is a local min or a local max. Okay? All right, that's all I have for right now. Thank you for watching.